exceptet.
Okay.
Alltså du kan ju på samma sätt bara köra liksom. Jag menar vanliga, du kan ju komma åt det lokala filsystemet. Så det är inga problem så. Precis.
Yeah, sorry I'm starting a bit late because I've had a lot of last-minute fires to field. So Ivan is currently in New Zealand. He's been helping with lots of little things. Thanks, Ivan. So we are live. But I think today we'll have one of you present the taxi stuff. So let's see. So can you send it to my Gmail or?
Yeah. What is your Gmail?
Just my first name, last name at gmail.com. So. So how about another student volunteer? So does someone want to try this Twitter streaming language classifier maybe, or something like this? Couple it with. You want to try it next time? Yeah, why not?
I haven't started learning, so I want something to pressurize.
Yes, to pressurize you. Good.
So maybe I'll take it.
Yeah, I think that'll be good.
When is the next one? It's not next
I think it'll be when we come back after the break.
So
yeah.
3 weeks, right?
Yeah, 3 weeks.
Yeah.
Yeah, no, it'll be good. And I think last time when we were discussing this, I thought it was only the top most frequent words will be used, but someone corrected me that it's actually a proper hash map, so it'll be a many-to-one mapping. But anyway, you can tell us all about it. Okay, so here is Victor's. There's your link.
Oh, I didn't. Yeah.
Okay, so
I just wanted to send you a mail.
So Victor will try and talk about the New York City taxi stuff, which would be awesome.
No.
Oh, okay, this is good.
Yeah, I didn't know how to share it by link. Is it the publish button? Or
yeah, I think it's a publish, but this is okay.
Yeah.
So just put it here and just pull it up to maybe the community edition.
how much storage do you have
on the academic shard?
I mean the community.
I don't know.
Because I was able to download the
Yeah.
2 GB file, but
Yeah.
am I able to do it on yours?
Oh,
No.
well, you don't have access to the academic shard, right?
No.
So if you can do it in the community edition, that's great. So let's just go here. So while we're here, let's sort of get this housekeeping out of the way. So okay, maybe we'll come back to that later. So let me just put it page notebook. Sorry, I have to import, right? Import file. BBC. So you probably already did all your. Did it take a long time
to download?
Yeah.
No, it went pretty fast.
Okay, good.
But I mean, I just got that part and I guess the results are still. Huh? What did you say?
Scala, it says on the top.
Okay. Yeah, so where do I begin? I started out by messing up. I downloaded the 2017 files from the yellow trip data, but they don't contain the coordinates for each pickup. So I downloaded it 2015 July. I think I'll skip this part because it takes some time. And then I downloaded the neighborhoods, which is in GeoJSON format. Not really sure why, but yeah. Okay, and then a lot of variables containing different paths. So this is for the distributed file system path, where I store the data, and this is where Databricks downloads the files after wget. Yeah, creating the path, copying the CSV file as well as the neighborhood file, importing Magellan packages and Spark SQL. And this was just to see that the file contains the right data. And it looked like it did, so I continued. Oh yeah, and the first comment here was for the 2017 file, because it was different, so I tried to customize it, but that didn't work out, as it didn't contain any coordinates. So
comment is shitty.
That's
good.
Yeah, it was real shitty. So here's the one that works. Yeah, should I the thing is to just casting the types for each column. Okay, and here comes the parsing and loading the data. So I guess it's pretty straightforward from here, but the schema, this part is added to the SQL context, and it's reading in CSV mode, and I guess this means that if a row is corrupt, it won't read it and just skip it. Not sure. Oh yeah, and this part is converting the pickup longitude and pickup latitude to Magellan points as we parse the files, and then we cache it because it takes some time. And then I wanted to make sure that the parsing went right, so I did a count. But I can see that it's not there right now. But I think it was some millions. Okay, and then I wanted to parse the neighborhoods. So afterwards, it was possible to make a join between the neighborhoods and the pickup data, and that's pretty much the same thing as with the trip data, but instead I use the GeoJSON. I'm not sure you have to correct me, but what does it contain? Is it Magellan points?
No, I think that's the information on the polygons of the boroughs.
Yeah. Okay, so it's more or less a polygon.
Yeah, GeoJSON is a format. It's one of the two major formats.
Oh, okay.
So I'll show you the shape format from San Francisco next. It's the other format.
Yeah. Okay, so yeah, this is the neighborhoods, and there are 310 neighborhoods. And this was just to check that it's all right, and this is where the joining begins. So I'll take the trips and then join them each by neighborhoods where the point of a trip is within the polygon of the neighborhood. And then I print the schema for the join table. And I think, yeah, so here's both of the points and polygons. And the last step, I think, yeah, is to take the join table and group by neighborhood. I'm not sure about this little symbol, but it is a symbol in Scala. Not really sure, but without it, it doesn't work, and it doesn't accept strings either. And then count the neighborhoods after they're grouped by, and then order by count, and here's the results. So Midtown has a lot of.
So these are actually, is this just the beginning and ending of the trips, or is it like every?
Yeah, I thought about that right as you asked, because I'm not sure if these are pickups or drop-offs.
Because if you look at can you look at the timestamps? Because I haven't read the blog myself in detail.
You mean the timestamps of
the raw
pickups?
Yeah.
Or the trip data?
Oh, so yeah, the trip data. So the trip data basically has pickup date time. Okay, so it's just pickups and drop-offs maybe.
Yeah, just pickups. Pickup longitude, pickup latitude. So Midtown has, a lot of pickups.
Right.
Yeah. I'm not sure if I made myself clear or just messing things up, but yeah, this is what I did.
It makes sense. But also, if you do this, by time and whatever time of day and things like this, there's a lot more information.
It would be interesting to see because they have some tip in the data as well. It'd be interesting to see what place that tips the most and goes the shortest distance. Yeah.
Okay, good.
Any questions?
So how long did it take you to kind of
to do this?
Yeah.
Like 40 minutes.
40 minutes?
Yeah. But it was it was a tutorial.
Yeah, sure.
Yeah.
Does 40 minutes includes the shitty stuff as well?
Yeah.
Oh, what's good?
50-50.
Great. Yeah, so I mean, I think, of course, it's just like some join that, you're supposed to be creative with the use of joins and spatial data. Later on, I'll show you something else, how you can take time intervals and make more formal objects, like spatiotemporal objects. And once you have space and time, then you can start doing more interesting things, ask questions. Was some person who got off the taxi at this location, and how far could they walk from in 15 minutes? Like, this is a basic question in surveillance. Uses the same technology basically, except you have a lot more details now. You just have some pickup and drop off. You may have like CC camera locations. It's a whole lot of stuff. Facial recognition, and those are very standard things. And then the fundamental primitives are once again spatiotemporal objects. So you basically take Magellan data structures and product that with time intervals, and then you have an enclosure of some object or person or whatever in space-time. Okay, so let me try to have kind of a plan. So I'm not sure. So I was trying to get you guys into LDA before we finish. I may not be able to go through all of it, but some of you are interested in doing more sort of textual work. So I thought we can do latent directly allocation a little bit if we have time. So let's see. So you can again just get the latest DBC archive. And I'll start from, let me start from here. So this is this is what I was trying to say last time. So we did quite a lot of work for this power plant data, right? We did regression, we did cross-validation, and this was ridge regression, which had a regularization parameter, some number that you multiply by the size of the coefficients, and then we can sort of choose the best regularization parameter by cross-validation. And then we found that the one we sort of picked out of thin air was just as good as the best one we found from regularization over a grid of 10 points. And then we said, okay, let's forget about linear regression. Now let's try gradient boosted regression trees. And gradient boosted regression trees are essentially an ensemble method where they try to recursively fit what wasn't fit before. And it's a very powerful method. And so to use it with regularization. So we did that, and what happened was our mean square errors improved a lot. So we were happy with it, and then the question is, how do you sort of deploy this? So we want to simulate a situation where queries are coming at us, and then we want to serve a prediction. So that's where we were. Anyway, this is all recall from before. So this is the decision trees, and then gradient boosted trees were even better. Yeah, so the mean square error is 3.76, and I think the best mean square error so far with the other methods were 4.6 or something like this. So we can keep improving this, but let's say this is good enough. And this had an ensemble of 120 trees. And this is how we got the debug string to try to make sense of the tree. And then the question is, can we, we worked hard, and in fact, this took like 6 minutes this morning to do all of the cross-validation and everything else. 5.3 minutes in a fairly meaty shard. So it will take a lot longer in the community edition. So then the question is, how do we persist this? So one thing we should kind of highly recommend reading this blog. So machine learning model persistence is very crucial. It gives us the ability to save and load models, first of all, across languages, but also across teams. So often in a sort of industrial setting, the data scientists will be playing with data, getting insights, improving the model, and things like this. When they're happy with it, you will sort of persist the model. Okay, basically a file. Turn it into a file, they store it somewhere, and then you can load from that file. And then the engineers, let's see what this blog basically says. A data scientist produces an ML model and hands it over to an engineering team for deployment in a production environment. A data engineer integrates a model training workflow in Python with a model serving workflow in Java. You can switch between languages and the right frameworks as well in this way. A data scientist creates jobs to train many ML models to be saved and evaluated later. So you can also save the entire cross-validation pipeline itself. So you can repeat it on the same training set, for example, in a different setting. So I think this notebook goes through the whole thing. So I think they do some training in Python. In fact, in the field, a lot of data scientists usually know Python or R. And then that's fine for lots of stuff. You can use PySpark, and then you can save the model, and then that's sort of handed over to a data scientist who loads it from Scala and then continues on. Okay, that's what this example does. Yeah, so yeah, this is all you do. You just do some training. Here's some random forest classifier. You fit the model, and then all you do is model.save, give a path to a file, right? And then you can just do whatever the model type is. So you call that same class, but you call the load method on it, just the path to the file. Okay, so it's just as simple as that. So, okay, so here's how you load it in Scala. Okay, so you can, of course, save and load full pipelines. So this is very useful if you want to replicate it. And I mean, when I interviewed for Netflix, it was an A/B testing job. I wasn't sure what I was going to do last year, and so in A/B testing, it's quite serious, right? So you really have to be a data engineering scientist. You cannot just be an engineer or a scientist. So you are getting your insights live from your recommender systems you're building to get more people watching Netflix or whatever, but you are directly sort of judged on how well you're performing with your new innovations with the A/B tests, right? So you will be improving on what your sort of others in your team have already built. So that'll be your sort of main model, you'll load, and then you'll try to improve it. And in A/B testing, basically what's happening, you would sort of try out your experimental innovations live on a small fraction of the actual real data, right? So you might try to have these tweaked recommendations, and hopefully it'll significantly improve on what's currently happening, and then you will sort of move your current model to that model. That's basically A/B testing. Okay, so let's do this. So I basically I wrote this already. So I simply saved this model into my distributed file store, the best model, and then I can just load the saved model back. Okay, just from the file that I wrote, which means I can start this notebook, jump directly to command 95, and continue from here, basically. Okay, up to the import statements and things like that. So, and then when I just looked at the same model that I loaded from the file, the debug string is the same. It's the same exact model. Okay, so now let's do a deployment. So I have my best model around, and make sure that's still here. And then what I want to do is to create a table for predictions. So I'm going to create a table called power plant predictions with all my features and my predicted output. So currently, let's still play with Spark Streaming. So we're going to create a streaming job to score the new power plant readings in real time and simulate some kind of a queue that sort of, we're going to just basically make our own queries just artificially, but it'll have a streaming context. So, all I'm doing here is creating a queue using RDDs of strings, and my batch interval is every 2 seconds. I'm going to be setting my batch intervals, and then my creating function returns a streaming context. So I have my usual Spark streaming context, batch intervals, and I want to remember, say, the last 300 seconds. And now when I have my discrete RDDs, I'm going to, for each RDD, I'm going to map the RDD, to while it's not empty, into my final model dot transform. And to the transform, I'm simply reading the JSON from data sets to data frame. It doesn't matter. So whatever I'm pumping in, I'm basically packaging it in the right way and pumping it into my final model. Because when I call the dot transform method on the final model, it will tell you the prediction of the features. Yeah, and then I'm just simply selecting the ones I want to report and saving it to a table. So let's run this. Some warnings, so we'll ignore for now. So now we've created and defined our streaming job. So let's first clear the predictions table. Now I'm going to add to my queue. I'm just taking my Spark context, making an RDD seek with this particular string. Okay.
So Ross,
yeah,
the lift web from the net package, you have to install.
Yeah, sorry. Yeah, so you have to install a little bit.
Okay.
Yeah, so you have to install the lift thing. I mean, I really should. I was advised by the Databricks guys to rewrite this to not use the net lift web and just use spray JSON, which is already in Databricks apparently. I haven't gotten down to it. I had more serious problems that actually I will help fix this morning, getting all of this working, because 2.1 is quite different. Yeah, so it won't work on your community edition, fortunately, right now. So yeah, so I'm basically creating a queue, you know, and I'm just sleeping for 5 seconds. And now I can try to select from my power plant prediction table and see what my prediction was. So it's only using the first 4 features to do the prediction. Okay. So, and I just pulled this record from the actual test data. Just to, there we go. So that's you know, that's a live update. So something came in the stream, whatever we artificially put in, and we're just doing a prediction in the live stream. So here's just another example. So yeah, we're just sort of simulating, say, every 5 seconds or so, something comes in, and we remember what happened in the last 300 seconds, and then table now should be updated to 2 rows. So this one should be. So of course, in a sort of real world or more real world situation, you will have much better designs. You'll probably have some kind of a Kafka queue or something that's spouting stuff at you, and you will interface to it. It's a lot of engineering. I'm still learning all this stuff. So, but this is the idea. Okay, so you can get into those things easier when you're in the right team. So here is so the predictions are very close to the real data points. So we can check that by just this SQL statement. So I'm simply going to the power plant table, the full table, and where atmospheric temperature is between 10 and 11, and pressure is between 1000 and 1010. And just around this neighborhood of values we asked, just to see if it's reasonable, if the predictions are reasonable in this neighborhood, and it seems so. So very, very important, we want to stop the streaming context and not keep it running. So that basically brings us to the full circle, right? This is kind of, you know, so you had some data. Okay, you didn't have to do a lot of cleaning in this particular case because it was already pre-formatted, but then you did some, you know, ETL, right? So what was all the steps? Let's recall quickly. So here's basically step 1 was sort of some kind of business understanding. You know, I don't know what your prediction job was in this case. So you have to predict the power output. Step 2 was to just load the data. Step 3 was to explore the data. So you're learning SQL along the way. Visualizing it using these pairwise scatter plots and so on. And then we prepared the data and we used the machine learning pipelines for all of this in an easily replicable, reproducible way. And then we did data modeling with not just one family of models, but multiple families, trees and regression and so on. And then we did tuning and evaluation. So we did, training and test, and the training itself we took away and did cross-validation. Basically broke that into really training and validation sets. We did threefold cross-validation, and to find the hyperparameters for each problem. So, so the regularization parameter for regression was this constant positive real number lambda for bridge regression, and I think it was what the depth of the tree was the regularization parameter for the ensemble method. I think. So anyway, and then we found the best model after cross-validation, and that's basically tuning. Okay. Then we took our tuned model, which hasn't seen the test data yet, and then transformed. Applied the transform method against the test data to actually see how well it did. Say in this case it was regression, so we did the root mean square error, right? That's how we compared across different model families as well. That's a standard recipe. That's exactly what you want to do, in this context. And then finally, we did like a baby deployment just now, right? So we simulated artificially data coming at you, and then you sort of have a stream set up, and you loaded the data from this file, and then you were just basically responding to queries. I think though, one other caveat, we haven't done alternating least squares or any kind of recommender systems yet, so we'll probably start next time, the second week, we'll definitely do that when we come back, because that's a very, very standard thing in data science. So often these, these sort of recommender system models, when you save them, they can be very, very, very huge files, possibly. So then you would just still be fine, because exactly the same save command will work, because you are saving in the distributed file store, so it will automatically scale up for you. And then once again, you load and serve. And we briefly looked into how data scientists and data engineers sort of work in this sort of pipeline way. Yeah.
So, for example, like what happened with them, assume that you developed a model based on data that you already had, but then another type of data came in after a year or so that had a different schema.
Yeah.
Like his, for example, they excluded something or added something.
Yeah.
So how do you don't train the model again on the new data?
Yeah. No, that's a great question. So, so first of all, it's good, because then you have job security, right? Somebody has to do the job. No, I'm not being facetious. It's true. So in fact, well, like when I started doing data science, right, like without knowing much, I would say 90% of the time we were doing this kind of stuff. We were like, it was hard work. You're just formatting and pulling this out and on and so on. And the pipelines have made this incredibly much, much, much better than it was before, right? Because you would be rolling out things that quite from scratch. Even when I was offering this course, pipelines came like literally when I was doing this course last year, so we sort of absorbed it. So that essentially helps you repeat things much more quickly in a replicable way. So for example, let's say the format changes, right? But your model may only want a subset of both formats, right? Say your model only relies on these 4 features. Maybe you have other features, or maybe one of the features is transformed in a deterministic way. Okay, these things are okay because you can bring that as part of your pipeline. It's just another transformation step you do. So that's good, and also your full plan of how you evaluated the data. Remember in that blog, they actually show you how to save the cross-validation pipeline itself. So you will have your grids that you set up, everything stored. And then you can plug in like a different, you can save the whole pipeline, which means you can plug in different, different data itself, right? So you can replicate your design.
So what if I designed on set of features, but then next year they deleted or excluded some features? Do I have to train, for example, we're not speaking about 1 million data points, maybe Netflix is a huge data.
Yeah.
So if, for example, they had a duration for the watching duration, but then next year they exclude it from the data, can you still make predictions and continue using the model, or you have to start again from scratch?
Yeah. So I don't know what Netflix actually does. It's all proprietary, but I would be super surprised if they delete things, because the standard way with data frames anyway is to keep adding more columns. So you would definitely not delete something that was useful, generally, right? But if,
for his example, deleted the
yeah, I don't know what's happening in New York City, okay, so I don't know. But they're not in the, okay.
I mean,
no, I agree. So if your company is sort of trying to sell some taxi information, like where you should go and stand at this time of the hour to maximize your chance of getting a taxi, yeah, you'll be screwed. you know, but at least you can save the historical stuff. I don't know. I mean, that's sure. I mean, but I think pipelines just makes things a lot faster too. So let's see. So I'll see if coffee is here. If not, I just wanted to quickly finish off this Magellan thing. And I have coffee. Tilo and Dan are here, so. Okay, so I think they're going to prepare coffee. So let's just kind of storm through this really quickly. What did I do? So yes, so to run the Magellan notebook, you should, I think I already showed you last time. You just had to download all those files and the San Francisco neighborhood files. It's all on the bottom, so you would have loaded it now. Then so I just so here's just the basic data structures are going to be command 8. Not sure. Let's see. It should work. Oh. Okay, so my cluster is terminated. So let's see. Let's see if I should be able to go into Community Edition and do this. Yeah. Yeah, maybe we should just have coffee. I'll just clean this up. Delete. Yeah, I'll just load up the stuff and then we can come back. Ooh, it's 4.6 now.